10.4, we're talking about determinants of a square matrix, which means if the matrix is not square, does it have a determinant? No. The only matrices that have determinants are square matrices. We're going to do 2 by 2 matrices. We're going to talk about minors and cofactors. And there's something in here called expansion by cofactors. I'll go ahead and present that, but I'm probably going to end up teaching it the way that I was taught. I did what was called expansion by minors, which is essentially the same thing. And then we're going to find determinants of square matrices. We briefly talked about a determinant of a 2 by 2 matrix last week. Do you remember? Down minus up, down product minus up product. That was useful in calculating, using that. We had a formula to calculate the inverse of a 2 by 2 matrix. And the formula to calculate the inverse of a 2 by 2 matrix involved 1 over the determinant times swap the DNA, change the sign on the B and C. Okay. Every square matrix can be associated with a real number called a determinant. So I can take a matrix and boil it down to one number, and that one number is going to be called the determinant. They have several uses. Several will be discussed in this section. One we actually talked about last week. Historically, the use of determinants arose from the special number patterns that occur when systems of linear equations are solved. Here's a system. A sub 1x plus b sub 1y equals c sub 1. That's just one equation. Coefficients are a1, b1, constant is c1. Second equation, a sub 2x plus b sub 2y equals c sub 2. Another equation. Coefficients are a sub 2, b sub 2, and constant is c sub 2. The solution, it has two solutions. X is equal to C1 times B2 minus C2 B1 divided by A sub 1 B sub 2 minus A sub 2 B sub 1. What's that bottom? That's the down diagonal minus the up diagonal, right? Okay. So that right there is the determinant. We can solve for y by a sub 1 c sub 2 minus a sub 2 c sub 1 divided by, oh, the same determinant. What happens if the determinant is 0? There's no solution, right? Because if the determinant was 0, we'd have something divided by 0, which is undefined. And we're going to revisit this whole equation right here in section 10.5. It's we'll be talking about some guy named Kramer. Okay. This denominator is called the determinant of the coefficient matrix of the system. So again, the determinant, down diagonal, a sub 1 b sub 2 minus the up diagonal, a sub 2 b sub 1, down minus up. Have I said down minus up enough yet?
Say it one more time.
Down minus up one more time. Okay, you're welcome. Okay, so if I have a matrix, a sub 1 b sub 1, a sub 2 b sub 2, I can calculate the determinant. Now, determinant uses what looks like absolute value bars. So if I write brackets, I'm talking about the matrix a sub 1 b sub 1, a sub 2 b sub 2. If instead of brackets, I just have the absolute value bars, I'm saying, hey, what is the determinant of this matrix? I'm not telling you this is a matrix. I'm saying, what is the determinant? And again, product down minus product up. Maya, you okay? I'm getting a death glare today.
I don't blame.
Okay. Questions so far, guys? Okay. DET of A, that is red determinant of A, or what looks like the absolute value of capital A. Those are used interchangeably. If I write it either way, I mean, what is the determinant of matrix A? A convenient method for remembering the formula of the determinant of a 2 by 2 is shown below. The determinant of A is equal to the down product minus the up product. Okay, enough of that. Okay, there you go. No problem. Good. Okay. The determinants of the difference. Let's say this another way. The determinant is the difference of the products of the two diagonals. So you take the down product and subtract the up diagonal product. The determinant can be positive. The determinant can be negative. The determinant can be 0. What do you know if the determinant is 0? What's that tell you? The matrix has, no inverse. The matrix has no inverse. The matrix has no inverse if the determinant is 0. If the matrix is a 1 by 1, then the matrix number is the determinant. So if I had a matrix of -2, then the determinant is -2. Okay. What is the determinant of matrix A? What do we do?
Put it in absolute value parts.
2 times 2 is minus what? Minus -3, right? Down minus up. 4 minus -3 is 7. What is the determinant? Who said wait? Okay. What is the determinant of matrix B? 2 times 2 minus 4 times 1 equals 0. What is the determinant of matrix C? 0 times 4 minus 2 times, I'm just writing it out this time. I'm just writing it out different every time. Down product is 0 minus the up product, 3. Answer is the determinant is -3. How hard is that? Pretty simple. Okay, so 2 by 2s are real simple. You good? Okay. So here's A and B worked out. Move it along. Here's C. Move it along. But what if it's not a 2 by 2? Thankfully, we're not going to do anything bigger than a 3 by 3. Okay, because to do the determinant of a 3 by 3, we have to do what I call, what I always taught was called expansion by minors. This text calls it expansion by cofactors. Doesn't matter. To define the determinant of a square matrix of order 3 by 3 or higher, it's convenient to introduce the concepts of minors and cofactors. Minors and cofactors of a square matrix. If A is a square matrix, then the minor M sub ij of the entry A sub ij is the determinant of the matrix obtained by deleting the ith row in the jth column. Want, right? Is that what you heard? Okay. The cofactor is simply the opposite of the minor. Yay. Okay. There, I know. In the sign pattern of cofactors, that we're about to see, I'll just show you the sign pattern. Here's.
Stop listening after cofactors and minors. I don't like to associate with people that are adults. And minors.
Okay. That is a very important little chart right there. Okay. So that's the chart we're going to use because you can use expansion by minors or cofactors, whichever term you want to use, by choosing any row and any column. Okay. It's best to choose rows or columns that contain zeros and ones. So let's make it easy. And you'll see what I'm talking about in a second. All right, y'all good with that? Okay. Find all the minors and cofactors of A. Okay. There are 9 minors. There is a minor for every cell. So this is what it said. Let's say that I wanted to start with row 1, column 1. To find the minor, so if I was going to make a minor, a matrix, if you will, what I would do for row 1, column 1, I'm going to ignore row 1, switch that. Ignore row 1, ignore column 1. What is the determinant of what's left? -1 times 1 minus -1 minus 0 is -1. Okay. To find the next one, ignore row 1, column 2. The next minor is going to go right here. What is the determinant? 3 times 1 minus 3 minus 8, -5. Let's move on. I'm not going to do all 9 of these, folks. Okay. Row 1, column 3. Down diagonal, 0 minus 0 minus -4 minus -4, +4. Okay. Then we would do row 2. Y'all good with that? Okay. And so, and in my life, I have never determined the minor of every single cell in a matrix. I've never done this before. I've chosen one row or one column and done it. And that's why I was getting for my determinant. But this is the process of calculating your minors. Okay, questions on this? Okay. With technology, there's no use for this method anymore. I mean, realistically. But if you don't have the technology, you use the determinant in calculating inverses. Okay. Okay. There's the one that did second row. Moving on. And if we keep going on and on and on and on and on, here are all 9 of the minors. Okay. Row 1, column 1, row 2, column 1, row 3, column 1, row 1, column 2, row 2, column 2. Okay. Okay. Cofactors. To find the cofactors, you're going to combine this matrix, if you will, with this matrix. Okay. I'm going to the next slide. Let's go back real quick. Okay. The cofactors. Nice. A plus means leave the sign alone. Okay. So if M11 is -1, then C11 is going to be, leave the sign alone, -1. If M12 is -5, I'm in this position now. What is C12 going to be? The opposite of -5 is 5. We're using this table, and it's always going to look exactly like this. It's always going to start with a plus. It's going to be alternating plus and minus signs. And all we're doing to convert the minors into the cofactors. And again, until this text, I've never seen this concept of cofactors in my life. Okay. If there's a plus sign, you leave the sign alone. So that's a -1. So it's -1. In row 1, column 2, I want the opposite sign. The opposite of -5 is +5. In row 1, column 3, I want to leave the sign alone. So that becomes stays a 4. Next row, the cofactor of 2. Well, I want the opposite of 2. So -2. 2, 2. Leave the sign alone. So -4. 2, 3. Change the sign. Molly, good? Okay. So again, the plus does not mean it's positive. The plus means leave the sign alone. So a minus means change the sign. A plus means leave it alone. So if we expanded that completely, we would have all of our cofactors, and all of our cofactors are here. Here are our minors. That's what we started with. Here are the cofactors. Questions on this? Okay. The definition below is called inductive. It's inductive because it uses determinants of the matrix of order n-1 to define the determinant of matrices of order n. If A is a square matrix bigger than 2 by 2, then the determinant of A is the sum of the entries in any row or any column multiplied by the respective cofactors. Okay. So for instance, the determinant of matrix A, they're going across, looks like row 1, doesn't it? Row 1, column 1, row 1, column 1, row 1, column 2, row 1, column 2. They're going across row 1. So I will do it their way. Let me go ahead and finish this right here. Okay. Leave it alone. Change it. Leave it alone. So what they're saying is, if we went across row 1, I want to take this value, so the determinant of A is equal to 0 times -1 plus 2 times 5 plus 1 times 4. This is the determinant. I'm calculating the determinant of this 3 by 3 matrix. And I'm using their method, which is called expansion by cofactors. You can choose any row or any column, you're going to get the exact same answer. 0 times -1, 0. 2 times 5, 10. 1 times 4, 0 plus 10 plus 4. The determinant of matrix A is 14. And that was calculated by going across row 1. I will now do it with, I'll do the determinant of matrix A using column 2. So I'm in column 2 for A, column 2 for C. So that gives me 2 times 5 plus -1 times -4 plus 0 times 3. Is it negative? Okay. So 2 times 5, 10. Negative times -4, +4. 0 times 3, 0. 10 plus 4, 14. It does not matter what column I choose. It does not matter what row I choose. The determinant of this matrix is 14. Questions on that?
Determinant formula.
That's the determinant on a 2 by 2 matrix. This is a 3 by 3. There is no formula for a 3 by 3. I just showed you every step. I did the whole,
Oh, it's that.
all of this is connected, yes. Okay, so I covered up a row and a column to get that number. I covered up a row and a column to get that number. I covered up a row and a column to get that number. Okay. Questions on this? Okay. I already talked about this one. So that method we just used was called expanding by cofactors. Okay. It says try checking that for a 2 by 2 matrix. This definition determines a sub 1 b sub 2 minus a sub 2 b sub 1 as previously defined. If I covered up this row and column, what's left? B sub 2. That's why I have a sub 1 times b sub 2. If I covered up this row and column here, what's left? So a sub 2 times b sub 1. This is in the minus position. That's why it's a minus. Remember that for this matrix, it would look like this: plus, minus, minus, plus. Okay. Okay. This is the exact same matrix. The question says find the determinant. I've shown you how the book tells you to do it. If it's okay with y'all, I'll show you how I was taught to do it and how I've done it for years. Is that okay? Just another method. Just another method. Because I want the determinant of this matrix, all I care about is one row or one column. And it doesn't matter which one you choose. Best choice, choose one that has zeros and ones. Since we've already done row 1, we've already done column 2, why don't we use row 3? Does row 3 look easy? It's got a 0 and a 1 in it, right? So remember our matrix: plus, minus, plus, minus, plus, minus, plus, minus, plus. We are going to use row 3. Row 3 starts with a 4, and I'm going to keep the sign of the 4. I'm not even going to talk about cofactors for the way I'm doing this, okay? I'm just ignoring that piece altogether. I want to keep the sign of that 4. So the determinant of A is equal to 4. If I cover up that, what's left? A 2 by 2, right? I'm going to go ahead and write it out instead of writing what the determinant is. I am going to calculate the determinant of that. So it's going to be, I'm left with 2, 1, -1, 2. The next sign is minus. So minus 0. I know there's no math here, but if I ignored that column and that row, what's left? 0, 1, 3, 2. The next one's going to be plus. That's a 1. If I ignore that row and column, we're left with 0, 2, 3, -1. Y'all following okay? Okay. Down minus up. 4 minus -1. -1. -1. That's it.